Friends, with great pleasure, I would like to welcome Dr. Shivaprasad, who is a scientist at Jawaharla Nehru International Center for Materials Science, who has kindly agreed to participate in the festival and speak on a very important topic, light harvesting for super efficient solar cells and LEDs. Sir, on behalf of the Bangalore Science Forum and on behalf of all our members who have gathered here, I extend a very cordial welcome to you. He is not a newcomer to the Bangalore Science Forum. Some of you might be knowing that every year we conduct summer school for high school students and 7th standard students. And it is such a heartening thing for we organizers. It may be difficult for us to get the speakers for Science Festival, but not for the summer schools. Celebrated scientists like Dr. Balram of Indians of Science and Dr. Shivaprasad and many other people from Ram District Institute and Indians of Science who know a little bit of Kannada, because Balram, he understands but he cannot speak in Kannada. They volunteer and they always tell us, don't forget my name. As far as the Summer Institute is concerned, that taking classes for those children and spending some time with them acts like an elixir for us, and we will at least become some 5-6 years younger every time we come to Bangalore Science Forum. It's easy to speak to an audience like this, informed audience, but to keep 7th standard students glued to their seat, enjoying the interaction, is something which requires a great teacher in all these people. In fact, it is customary for us to read out a biodata with their achievements, awards, and all those things. Just a few of them I will mention. But I especially want to mention this particular attitude of the scientists in Bangalore who have been of such great help for organizing summer institutes and other things for graduate, undergraduate and secondary school students. This is one thing I wanted to specially mention, sir. And Dr. Y.C. Kamala is here, who is the organizer of this Summer Institute. She was always telling me with great pride how it was easy for her to get scientists of the caliber of Dr. Shivaprasad for those Summer Institute. Needless to say, in fact, he is a PhD in physics, speaks eloquently about his academic achievements. Right now, he is a professor, International Center for Materials Science at Jawaharla Nehru Center for Advanced Studies. He was a scientist working in the field of surface physics and nanostructures in the National Physical Laboratory, New Delhi. His field of specialization, surface science, epitaxial films, nanostructures, etc. He has published more than 160 papers in national and international reputed journals, attended conferences and invited talks. I'll just mention one or two awards. Here's a whole list of awards what he got right from 1992 onwards. The latest one being C.N.R. Rao Oratory Award in the year 2011. Rack Camp Senior Fellowship in February 2010. Like this, including Commonwealth Postdoctoral Fellow, he has a lot of research experience. He's traveled abroad and worked in various Asian and Western universities. More than that, this is one very important thing as far as Indian research is concerned. My brother and sister-in-law over here, they are complaining, fine, we have Indians of Science, IITs, PAITs, Ilani, and all these things we have visited. But unfortunately, all the professors there, they are research scholars. They don't have experience of interacting with the students because the feedback will come from the students. I have seen in California, Berkeley Institute, Nobel laureates taking BA classes. Physics is one subject. They are not regular physics students studying mathematics, etc. They study economics, language, music. They opt for one semester physics. I have seen in Berkeley, they are taking classes for such students. It is a wonderful experience to be a teacher. Unfortunately, we working in colleges and universities, we don't have any opening towards research, nothing. Bangalore University, Karnataka University, whatever it is. These days some bits and here and there some research. No emphasis, only classroom teaching. And there, no emphasis on teaching. But he has a teaching experience in the Department of Physics in USA, PAITs Pilani, for PhD students and others, National Physical Laboratory, MS and PhD students. And right now, of course, I asked him how many students are there in your research wing. Something like 350 to 400 students are there. This is a welcome change as far as higher education in India is concerned. He has so many laurels. I don't want to take your precious time on a rainy day, but an extremely competent person to come to the Bangalore Science Forum. And we in Bangalore Science Forum, and I'm sure that all of you will agree with me, it gets credibility because of our association with such great scientists like Dr. Shivaprasad. On your behalf, on behalf of the Bangalore Science Forum, I extend once again a very hearty welcome to him and request him to give his talk now. Dr. Shivaprasad.
Good evening, friends, lovers of science. Usually I talk until 50% of the people are sleeping. That is how I decide how to talk. So to just know when people are sleeping, can I request people sitting in the back to come a little bit front, please? So that I will understand when you are actually sleeping. Now the idea is that there may be some small things I may show in my presentation which may not be visible from the back. So may I please request you to come to the front. Actually, normally all the atoms fill from the inner shell to the outer shell, so let's fill all the shells inside before we can do it. Okay. Somebody made one step transition. Good. Okay. Right. It's such an honor to be here, to hear of the wonderful thing which was started by the great HM, to be here. But more interestingly, I thought I'll come here to teach you something. But my last 40 minutes in the principal's chamber was an amazing education to me by talking to Professor Ramakrishna Rao. I mean, he educated me in so many things. It was so exciting talking to him. I thought, let me continue this for 1 hour rather than him making me listen to my boring lecture for the next 1 hour. thank you, sir, and Mrs. Kamala, for giving me this opportunity, and Dr. Ramarao for giving me this opportunity to share some of my things with you. As you know, this year is called as the Year of Light. Okay, this is because of Inbal Patton's book, the first book, the Treatise on Optics. Amazing thing which he did 1,000 years ago. I mean, all the concepts of refraction, diffraction, everything were done on that. And as a respect to that, this year has been called as the Year of Light. So, I have an opportunity to pay my respects to him, of course, and then to this great man, which we all, unfortunately, I did not have the opportunity of seeing him, but as children, as students, we were so inspired by his presence, just that he was somebody in Karnataka. He was, I mean, the amazing things he did. I mean, absolutely a nationalist, absolutely a rationalist, and then he spread the scientific temper among everybody. So I find this as an opportunity to pay my very, very deep, sincere respects to him before I start my talk and tell you. So let's start from the beginning. Of course, the beginning is, I'm sure a couple of you may have heard this talk when I talked to the children, and the beginning there was the same as the beginning here, but I hope the end here will be different from the end I had there, because I'll probably show you. But before that, I should tell you, this particular picture is a wonderful material we have made recently of gallium nitride, on which silver nanoparticles have put. This is only a few months old result, from which we have produced that material which we are looking for making super efficient LEDs and solar cells. So hopefully at the end of the talk, I'll tell you why we made this material. Okay, so before that, let's start from the beginning. As I said, light shines on a material. We all know that. When light falls, white light, sunlight, say for example, any light which we call as white light, falls on an apple, the apple absorbs all other colors, and it reflects the red color. It does not like the red color. And that is why we see it and we call it as a red apple. Same thing with your blue shirt, your red shirt, your green shirt. There are dyes which absorb rest of the colors, and this color, that particular color is reflected. So this is called as a reflected color when we see on the material. So when I put the light, some of the light gets reflected, like in this case. Some of the light gets absorbed by the material, because there are something called as electrons in the materials. And those electrons absorb this light. And we'll talk about it more, okay, of how the light is absorbed in these materials and what happens to this absorbed light. And then we have some light which can be transmitted through the material. So we all know that if it is reflected, we see these opaque things or the metallic things especially. And if it is transmitted, we call it as a glass, a transparent material. And then if it is absorbed, things can become hot or do something. We'll look into that. So now, let's look at the material. As I said, one of the important things of these materials are we have to divide how the electrons are distributed in the material. So I like to give this simple analogy. So there is if I take a material, there are three kinds of material, you know, the conductors, the semiconductors, and the insulators. Right? You are all familiar with this. So what is happening inside these materials? Why do we call something as a conductor, why something as a semiconductor, something as an insulator? The idea is, there is these green boxes which are basically the houses of electrons, or we call them as the valence band of a material. And also, I'm not talking about the inner electrons, we are only talking about the top electron, outermost electrons in a particular atom. So these are the house of electrons, that's where electrons are housed. And then we have these blue boxes which are called as road for electrons, the roads of electrons, and they are called as the conduction band, means where electrons conduct. There are no electrons in the conduction band, but there are well-made roads, well-defined roads. And when the electron is also sitting in well-defined houses, which are called as the valence band. And so, if some energy is given to these lazy electrons which are sitting in the valence band, if they get enough energy to go over this barrier, means to cross the distance, energy distance between the house and the roads, they go to the roads. In an insulator, for example, the roads are very far away. You can't give enough energy for the electrons to go to the roads, they continue to stay inside the houses. And that is why we call them the insulators, they don't conduct. So you can easily make a plastic, a wood and touch electricity with them, nothing happens to us. Because the electrons, there's not enough energy for them to get excited. Because the distance between the house and roads, which we call as the band gap of a semiconductor, is very large. Now let's take the conductor or a semiconductor. Semiconductor is a small, the gap is small. That means the electrons on their own don't go to the roads, but if somebody kicks them, they are ready to go to the roads. So how do you kick them? You can kick them by putting voltage, or you can kick them by heating, or you can do it by friction, or some form of energy which excites them and tells them, look, you have to go to the conduction band. So once they go to the conduction band, the material or that material or the semiconductor starts conducting. Means it becomes like a metal. So that is a semiconductor. What in case of a metal? There is the roads, the houses are in the roads themselves. So there is no need, the electrons are all there on the roads, you just put a small voltage, they start conducting. That is why the conductors, so you can't put a thin conducting wire into an electric plug because you will get an electric shock because of this. So this, what happens to this material? So this is how we define. And that's why the resistivity of this material is very low and the resistivity of this material is very high. So this, to just give you some numbers to get an idea, I'm sure some of you know about it. Of course here the band gap is 0, since there is no band gap in this material. In case of an insulator, for example, glass or some heavy insulator, the band gap is 5 electron volts. Right? So this is 5 electron volts. And then in a semiconductor, it is small, means it's of the order of 1 to 2 electron volts, so that we can make this excitation possible. So now let's see what happens when we put light onto these materials, a white light onto these materials. Obviously, I show a white light as a composite light of all colors, and you can see I put this on the conductor. So that when the electrons, when the light, means which actually contains what are called as photons, the photons, when they come and hit the metal, okay, they can excite the electrons because there are a lot of electrons available, but there is no place for the electrons to go because they are already on the roads. And that is why what happens is those electrons only oscillate but don't allow the energy to be absorbed. And that is why this light gets reflected from the material. That's why all the metals are shiny, a metallic luster, you know, and when you put a light, you don't, and it behaves like a mirror. The polished metal is like a mirror, beautiful mirror. Of course, there are colors for the metals. As you know, one of the famous material, the famous metal, with the famous color is the yellow color, which is gold, which we all want to collect, right? So, especially the women. Okay, so, and then the men try to get it. So everybody is busy after gold. So, why this happens is, now, in this case, the electrons are when the energy is given to these electrons in these materials, the electrons start oscillating from higher energy to lower energy. They have no place to go, but they just oscillate in their own presence. And they do it in groups. And these groups of electrons are called as plasmons. So the plasmon excitation, the plasmons get excited, they go to a higher energy, come to a lower energy, higher energy, lower energy. That energy difference creates photons of different colors, and that happens to be in the visible range of yellow in case of gold. And that is why the gold becomes yellow in color. But let's see now, if you strike it on an insulator with a very wide band gap. Like for example, the question, simple question, why is the glass transparent? Glass is made of silicon dioxide. That means silicon and atoms are sitting very close to each other. It's not like water or gas, because gas molecules are transparent because they are so far away that the light easily transmits through them. But in case of glass, they are actually sitting very close to each other, but still it is transparent. Why is it? Because my band gap is very large. That means when the light falls on it, there is no electron which gets excited with the visible light we have. And because you cannot excite anything, that light just transports through the material, and we call it as transparent. Right? So, but what happens in a semiconductor, as I told you, the band gap is reasonably small, that when the light, even visible light falls on them, the electrons get excited. Right? So we say that the light gets absorbed by the material because the electron take this energy and go to this conduction band. Right. So now let's look at it a little bit carefully. So you all know that semiconductors, you all heard of semiconductors. Of course, the most famous ones are silicon and germanium. But you know, how does it form? It forms from this beautiful periodic table. You know that group 1, 2, 3 and 4 have electrons 1, 2, 3 and 4 electrons in the outermost shell. That means to get that lazy form of getting 8 electrons in the outermost shell, they just have to give out this 1, 2, 3 and 4 electrons. Because say for example the group 1, if to get outermost shell of 8, it has to give 1 electron rather than get 7 electrons, which is more expensive. So that's why the first group 1, 2, 3 and 4 give out electrons, and that is why they are called as metals. And group 5, 6, 7, to become 8, it is easy for them to get electrons. That is why they are called as non-metals. Right? So, but what happens to this group 4? They're confused. 4 electrons in the outermost shell, it doesn't know whether to give electrons or to take electrons. And they are called semiconductors. So anything which is confused is a semiconductor. That is very important. So what I wanted to tell you is people who are also confused are very useful. Okay, right. So now let's look at the band gap. I told you I showed you boxes of electrons and the roads for electrons. But as we all know, nothing is so straight. All our roads are teda-meda. You know, they go this way and that way. Similarly, the electron states are also very, very confused. Okay, they are all going in different directions, different forms. So this I call it, I don't want to draw the whole band picture because of course there are specialists who work on these band pictures. I am only taking a part of that band picture. So I take this bottom of the top of the valence band and I take up the bottom of the conduction band. Means the top of the house, the nearest to the road, and the other one is the nearest part of the road where we would like to go. So when I look at that, so then I have two kinds of semiconductors. One in which, see this is a diagram where I can tell you this is momentum on this axis and this is energy. Because to define a particular particle, only energy is not enough. We need to know the energy and the momentum, then we are able to define everything about the particle. That is why we plot what is called as the EK diagrams in solid state physics. And this is a consequence of quantum mechanics. And the roads are like this because we know that the path of electrons are all waves. So now we are interacting the path of electrons to get this particular picture, and this varies from material to material depending on how many electrons are there, how closely they are attached to each other, and how the structure of the solid is formed. So now as you can see, the electrons, when they get excited to this, it is so easy when I get energy and goes without changing momentum. So these materials, where it can easily change only the energy and not the momentum, are called as direct band gap materials. Because there is direct transition in the energy scale. Because you know that physicists, we all talk only in terms of energy. Anything you give, we ultimately convert it into energy. And that's what we do and try to do it. So we make it very simple because we want to understand only one concept, and that is energy. That is the idea we make this diagram. So this electron may be anywhere in the solid, but if it has the same energy, I treat it as equal. That is the idea. Okay. Then there are other materials, like for example silicon. Silicon, this energy, this is not the nearest road. The nearest road is somewhere else. So it can go here by changing its momentum also. I not only need lesser energy, but I need also a momentum to make a transition. This is called as the indirect band gap semiconductor. The idea why I am trying to tell you is, see now look, so somebody else has to, other than the energy we give from here, some other energy has to be added to change the momentum also. And that comes from, because this electron is moving in a solid, and we all know that the solid, the atoms are not quiet. They are vibrating about this. And this vibration is called by a quantum mechanical phenomena called as phonons. So the atoms are vibrating and they are phonons. So when the electron is going out, it is also getting energy from the phonons. And that is how it is also able to change the momentum. And so it can make this, it can make this transition. But one thing is interesting you can see here. So if the electron goes here, then it will think, what should I do? Right? Now, if possible, like all of us, it wants to be lazy. So either it continues to go on the road, then we go onto the road, or we have enough excuses to come back to the house and sleep. The electrons in the direct band gap semiconductor, because they require less energy to come back, they would like to go back. And of course there are high energy electrons, when they lose energy, they come to this low energy state. That means that difference in energy gets converted into light. And that comes with as a photon. Photon means that gives you a color of light. And the color of that light depends on this energy, because E and lambda are well related. We know that E is equal to hc by lambda. So when the energy of this gets converted into a certain wave. So different energy has different wavelength and it has different color. That is how we look at wavelength. Right? Color for physicists is either wavelength or energy. Now, So this electron comes here with this energy depending on the band gap. So the color of this light will depend on the band gap. This is an important sentence. So the color will show, we'll talk more about it a little bit later, but I just tell you that the color. So now, but if it goes here in an indirect band gap material, it thinks, my God, it is so difficult for me to go back, because not only I have to lose energy, but I also have to take the help of phonons to come back. Because to come back also it needs energy to come back, because it has changed its direction in the K space. So that is why it will say, no, I'll stay here itself, so it travels on the road. So the direct band gap semiconductors tend to come back home and give up light. But the indirect band gap semiconductors don't want to come back, they stay on the road and they give electricity. Because they travel on the roads, when electrons travel, that is nothing but electricity. So that is very important to understand. That means direct band gap materials like gallium nitride, gallium arsenide, I'll talk about it a little bit more, okay, of that, but you can get light out of them. That means they are optoelectronic materials. You can make electrons which are giving optics, light out of them. So these become good optoelectronic materials. But look at this, silicon. Silicon does not give light, because if you like to stay on the road, it gives electricity. So it is an electronic material and not an optoelectronic material. That is why when you give light, you can make an LED, a light source, out of a direct band gap material. But you cannot make an LED out of silicon, but you can make a solar cell out of it. Because you need electrons flowing so that you can get the current out of it. That is how a solar cell works. Now let's see. So we had, by nature, has given us only two semiconductors, silicon and germanium. It is very unfortunate. If that was true, we would have very limited applications. Right? So man is obviously not satisfied. We want to do more. So we wanted to create more semiconductors. So how do we do that simple logic that we have to make an element confused, a material confused, with 4 electrons in the outermost shell. So this was group 4, it was naturally confused. So now we induce confusion by combining metals of the group 3 and the group 5 together. What is the average is 4. So you confuse them. So you take a material like aluminum, combine it with nitrogen, you get aluminum nitride, aluminum phosphide, aluminum arsenide, aluminum antimonide, gallium nitride, gallium phosphide, gallium arsenide, gallium antimonide, indium nitride, indium phosphide, indium arsenide, indium antimonide. So many semiconductors. So like that I can do with even group 2 and group 6. Again more elements. So you get many semiconductors you can form, which are, some of them are direct band gap and some are indirect band gap. I'll not go into the details of that, but just tell you that these are man-made compound semiconductors. The two we knew were elemental semiconductors, but we need many compound semiconductors. What do I mean by a semiconductor? As I told you, the most important property, among others, is the band gap. So when I say I make a different semiconductor, that means I make a material with a different band gap. So each of them have a different band gap. That is very important. So now, see, obviously when I told you that the light comes out of, depending on the band gap, the color of light, now I can get so many more colors because I have so many more semiconductors. That is very important. So now let's look forward. Now let's see how the LED and the solar cell works. So as I told you in the previous, if it's a direct band gap semiconductor and the electron comes down, it gives light. Okay? So obviously I can make an LED out of it, light emitting diode out of it. Or a laser. This is a LED, LD. This is a laser diode which is giving out green color. Okay? Or you will see nowadays LEDs are everywhere. White LEDs, colored LEDs. We all know that when we were old, we used to see only red LEDs, green LEDs, yellow LEDs. Only in the last 10 years, we started seeing blue LEDs. And in the last 5 years, we have started seeing white LEDs. Okay, so that is what is happening. So now let's see how a LED works. So I have this semiconductor. Only I know that I need to create electrons and holes. Holes means where the electrons went up, then there were holes in the valence band. So they have to be attracted. So now I have to do that. But I have to do it very high proportions so that it works very efficiently rather than one material. So what I do, I collect all the electrons on one side and I collect all the electrons on the other side, the holes on the other side. So this, I call it as an N-type semiconductor and a P-type semiconductor. We all know that you can do this by simply doping a material next to it in the periodic table. So once you do that, we have N region and a P region. That means I have N region and P region, then I put a voltage across this. I put a voltage in such a way that the holes move in that direction and the electrons move in this direction. So this is one side there are holes, these are electrons, I make them move towards each other. What is called as the forward bias. So when I do this, then the electron and holes are very proximal, which usually happens in the colleges when a boy and girl meet. They get together and form and they marry and they live happily married ever after. So there is a recombination of the electrons and the holes, and when they recombine, obviously as I told you, after marriage we also produce something. So this also produces light. Right? The light. So this is how an LED works. So you create electrons and holes which are separated, bring them together, combine them, and when they combine them, the output is light. And that's how an LED works. Simple. Now how does the solar cell work? Again, this is a PN junction, the same material. Only thing, as I told you earlier, one is a direct band gap material, other is an indirect band gap material. So I can have this. Now the husband and wife are living very happily together in this material, but we put a reverse bias. That we remove the hole and we separate the hole in the electron and pull them apart. So we encourage divorce. When you encourage divorce and you get this, all the arrows here will become directional, then we get electrons and holes moving in this circuit and giving out electricity. That is how a solar cell works. Right? But it is basically the same concept. You should understand. So, based on this, many kinds of LEDs were made. As I told you earlier, all the red, green, yellow, amber LEDs, all the LEDs you see on these machines were all we have seen earlier, but the blue was not made. Okay, so that was the revolution recently. I'll come to that. And this revolution was done by Suji Nakamura. In fact, last year, November, he got the Nobel Prize for inventing the blue LED. Because of the year of light, they thought that it is a great opportunity to give him, we call him the modern Thomas Alva Edison. Yeah, I worked with Suji for a long time, and he is a wonderful, wonderful scientist. But at the same time, he is now in the Santa Barbara, University of California, but actually when he invented this, he was in the Nichia Corporation in a small company in Japan. It's a very interesting story. I won't tell you the story right now, but I should tell you, you should read about the story. The reason why he chose this material was absolutely stupid. Okay, and he is very honest in telling what he tries to do. And the reason he worked, and then the way the company treated him was absolutely stupid. But ultimately, he had asked for something like $1 lakh to make this material, and the company refused. Okay, and ultimately, when he made the patent has earned him probably nearly, I think, more than $1.2 billion now. And the company was so stupid that it did not recognize this. So, but that is what the Americans, that quickly pulled him out, and now he's working, and he has a company of his own in America, working, etc., but also working in the University of California, Santa Barbara. So what he did was, he made this called white blue LEDs. Because red and blue, see, ultimately, eventually, what is our aim? We want to replace the white light, the light we get, with LEDs. Because these lights are not good enough. Okay. I have not put this because of lack of time. I did not put that. I wanted to show you. Initially, we started light with burning fire, and that used to be very, very inefficient. Only 1% light. Rest all energy would go as heat. Then we got the bulb, the Thomas Alva Edison bulb. One invention which has not changed over more than 100 years. It still remains the bulb. Okay, that bulb, it is only 5% efficient. Very, very inefficient again. Then we have these tube lights and CFLs. Okay, they are about 20% efficient. That's why we kept telling, please burn, don't remove the bulbs and put LEDs and CFLs, you will save power. But then I can show you, and again I should have put that slide, but it's okay. I just want to tell you, to give a number for the tube lights, they work at 70 lumens per watt. If you give 1 watt of energy, they produce about 70 to 80 lumens of light. Okay, so, but you know that making them is very difficult because of, and also environmentally not very good because you use mercury, which is not a good thing. So we want to replace it with a more efficient material, and that's why we see LEDs as a great opportunity. So LEDs are solid state, no filament, no vacuum, so they work very well, and they don't burn out. You buy one, forever it lives with you. Okay. Second thing, it consumes about 1/10 of the power it should consume. Right now it is not so much. I'll tell you the reason why. It consumes very, very less power, so which is very nice, environmentally friendly, and it is very fast. It is a semiconducting process. It is not like a heating process in a filament. So that's why it is extremely fast, very good for many, many other applications. So like that, there are so many advantages. More than that, you can get a very high quality of white light. Right now, you look at any light, it is never like sunlight. color is very different. It is never like sunlight. So eventually what I want is a small sun in my house, on my table, so that the quality of light is same. Now as I keep giving this information, I think fortunately there are not enough ladies who will be able to attack me, but I just want to tell you that when ladies buy saris, they are not satisfied with the color they see it in the shop. They will bring it outside and see it. So we want to make an LED so that they can see it inside and still get the same color. So getting this white color, the perfect white color, is also a challenge to get this perfect white color. So let's talk a little bit more about that. So now let's see. Okay, now let me go. So I can make, now we know, it is using a semiconductor, a direct band gap and indirect band gap. I can make a LED and a solar cell. We know about that. But you know that the solar cells we use now are made from silicon. Okay. Silicon has a band gap of 1.1 electron volt. That means a fixed band gap. So it will tell, so that is why the efficiency of a silicon solar cell is only 29% to the maximum. You can't get a silicon solar cell giving more than 25% efficiency. Because I have only one band gap, what can I do? I can do only this much. Right? So that's what it says. But you know, commercially, even the best solar cells are only 12 to 13% efficient. They are not even 29% efficient. That is why to get a little bit of light, you have to put miles and miles of solar cells, farms of solar cells. Very expensive. Only because the government subsidizes, we think that it works, but actually it doesn't make sense. Okay. But at the same time, it is good because we don't use the conventional power. There is a non-conventional support for this. It is not a very sensible thing to do. So what we would like to get is a 100% efficient solar cell. Can I get a 200% efficient solar cell? 300. And as greedy as he is, we want to look for more and more efficient solar cells. Is it possible? We think we go outside in the hot sun and tell, instead of burning me, let me produce electricity. How can this be done? What do I mean by 100% efficient solar cell? That means I put 100 photons onto the surface and I get 100 electrons in return. That is my 100% efficient solar cell. Why am I not able to do this? As I said, with silicon, I can get even the best possible. Theoretical value is only 29% efficient solar cell. Why is that? The reason is because the band gap is fixed. That means all the other energies, other than the, more than the band gap energy, are wasted in this material. So what I want to do, this is my solar spectrum. If I look at the spectrum on the solar scale, actually it is on the log scale, so it looks fast, but at the same time it is very, very well stretched. You can see there is a visible range, and then there is an infrared and the ultraviolet energy which comes around. Lot of energy comes from the sun. And then you have these peaks, this falls in the peak. This is because of absorption in atmosphere. We will not talk about it. But a very nice picture. That is how you can see and look at the ozone hole and other problems in the sky. Okay, so this is my solar spectrum. So now silicon only occupies some part of this part of the spectrum. It converts only that light because the band gap is only 1.1. So now I have an idea. I told you, now we have made materials of different band gap. Right? I know I have materials with different band gap. So can I combine? I tell this fellow, 1 band gap, 2 band gap, 3 band gap, 4 band gap, 5, 6, 7, 8, I can put as many band gap materials as I want. If I put this together, I tell this fellow, you please convert this part of the solar energy. This fellow, you convert this, you convert this, you convert this, you convert this. So like that, I can convert the whole solar spectrum. Right? In fact, I have shown these as boxes, but I can actually make a graded material which can change the band gap from one end to the other. So these are called as multi-band gap tandem cells, solar cells. And these, so what happens is all of them contribute to this, to the solar cell efficiency, and so theoretically you can get 100% efficient solar cell. I'll later show you how you can get a 200, 300% efficient solar cell. Okay, so now if I get probably a 300% efficient solar cell, if it works very well one day, okay, then probably I can just put a rooftop of solar cells in my car and run the whole car. It may be possible. Or I put a small solar cell in the house and also you can do water heating, which I can't do now. Right? So, and I can probably give enough to the grid. I don't need the grid at all. These kind of solar cells. So that is one of the dreams of what people work in this area. So now, right now, as I said, the white LEDs which are there in the market, including the flash of your mobile phones, okay, are also made from this kind of material called as gallium nitride. I'll come to that in a while. The gallium nitride is the material you get that. That is what gallium nitride is, the one which Suji Nakamura invented. He found how to make blue light out of that. And once you have this blue light, now it is very easy to think, I can mix the blue, all the primary colors and get white light. I can make all colors and get white light. So I can get the color I want, I can tune the color I want. I can get a perfect sunlight here. So these kind of options are possible. But right now, still it doesn't exist. Even the white LEDs you have are only actually blue color LEDs with some yellow phosphor color coated on top of it. If you look at the mobile very carefully, you see a yellow color, or even the white LEDs very carefully when it is off, don't see it when it is on, because there are still some small amounts of ultraviolet light which comes out of this, unfortunately, but there are good LEDs don't do that. But if you see that, there will be yellow color, and this is because of yellow phosphorus. And by light reduction, color reduction, you can actually create the white light. That is how it works. But eventually we want to make red, blue and green LEDs. This problem is not yet happened because there is a problem in making blue LEDs, the green LEDs. Green LEDs have a problem, which I'll probably, hopefully if I get time, I'll end up with my talk with those problems of green LED and what we are tackling on that. But making green LEDs is difficult. It is not stable because it requires a metal called indium, which is a little bit unstable. Okay. So let's see. So this is this LED story, and this is the solar cell story. The same thing, I can make an LED like this and get white color, beautiful white color. So that is how it goes. But solar cells are not made like this. Why? Because the method of making this is very, very expensive. It's so expensive and exorbitant that large area applications, people don't want to use this material. So that's why they use silicon. It still works out well and it is cheaper. So again, we are also thinking of making methods cheaper for this material, but I will not tell you today why it is very, very expensive. But it is still used in something like where people don't care about money. There are some of us who don't care about money, right? Like in space applications. When you want to carry a satellite, you need a solar cell there. What is important for you is the weight has to be less and the area has to be less. That is more important than the cost. So that is where they use these multi-bandgap tandem solar cells right now with the 44% efficiency solar cells where they use it. Okay, and there are military applications where they use this, again where they don't care about money, because they take our taxpayer money and pour it there, unfortunately. But we also don't mind. Okay, so that is how it happens at this point in these solar cells. So now let's look at it. So what is the problem? Why are we not getting this? So we know the process, we know what should happen. I just have to put semiconductor materials together. But what is the serious problem? There are a couple of simple problems which are not being able to be challenged. These are not engineering problems, they are scientific problems. And that is where the last 50 years people have been struggling. The improvement in the efficiency of these materials is only very by tiny steps. It's not making a major breakthrough in this material. The reason is that to grow this material called gallium nitride, there is no particular substrate. Because what you want, you have different layers, and you want the color of one layer to go through the film, the other color to go through, so you have to make layers so thin that the light can transport through. And at the same time, or in a solar cell, it will be absorbed. So different layers have to absorb different layers. So how do I have top layers and make them not absorb a particular light? And this is a challenge. So when you make this, so you have to make very, very ultra-thin films of the nano dimensions of these materials. So when I make these films, ultra-thin films, one after the other, then there is a problem. To make these films, I have to grow it on a substrate. Unfortunately, there is no good substrate available. The sapphire is the best substrate with all properties. Again, so you use sapphire. But when you use sapphire, the atom size, the distance between atoms is different in sapphire and in gallium nitride, as you can see here. So if you have 10 atoms here, there are 11 atoms here. So this mismatch, what we call as lattice mismatch, the distance between atoms, creates a lot of stress in these materials. Because atoms are not compatible with each other. They don't have a proper place to sit. They are not comfortable. The coordination number is not the minimum, is not the maximum. So they tend to have stress in the film. And these stress end up in forming dislocations. So the material dislocates this way or it dislocates this way. If it dislocates this way, we call it as an edge dislocation. And if it dislocates this way, we call it as a screw dislocation. So we get these kind of dislocation in this material. So now when I form the film, I form this film. Now what I'm showing is all the results from our laboratory. We form these films, a flat film, It looks very flat, but when I zoom it in, I see these dislocations, the defects in this material. If I see from the side, I see these defects in the material. I try to form it in the perfect way possible, but still these come just because of the lattice mismatch. The strain and the strain relaxation process in the lattice mismatch. So that gives you a lot of defects in this material. And obviously, more the defects, less the efficiency. Because the reason is that if you form, as I said, valence band or reduction band, there are rods. Now I create in between some barriers of the rods. And they are called as defect states. And these defects are coming from those dislocation states. And that is why you will get some defect states. So my electron will not make a transition here, it will just go here. And it will come down from here and it will be a different color. Right? Or it will go and just be lost in that defect. So you can imagine if the electron has to flow through these defects, it's very difficult. So that is why there is a problem in these materials. They are not very efficient. So how to make this material efficient means by defect free. How to make it defect free has been a challenge for the last 10 years, approximately 10 years. And we are also part of this game which we play. So now let's see how to solve this problem. There are several methods which are adopted, but there is a new method. Now it is fashionable to use nano for everything. And we also use the fashionable word nano, and except the nano car, which has nothing nano about it. Okay? So now in the nano is very interesting. There are different ways how nano is looked into. I have my own perspective of looking at nano and I would like to share it with you. Now we know that there is an atom. Inside the atom there is a nucleus and then electrons revolving around fixed orbits. The difference between planetary motion and atomic motion. In planetary motion, I can put a satellite anywhere I want. Right? It only centrifugal and centrifugal forces have to match. That's all. So I can get it in any orbit. But in case of electron motion, I cannot put them in any orbit because they are so tiny that you can't see electrons as particles now. You have to see them as waves. And once it's a wave, then my wavelength has to match. It is like imagine a wave of a snake. And if you make it into a circle, the snake has to catch its tail. If it cannot catch its tail, you cannot form that circle, complete circle. And that is the reason why electrons, you cannot form orbits wherever you want. So you will have only integral multiples of the wavelength that you will get these kind of waves. So that means each orbit has a different energy. So I plot this energy, again as I said, we convert everything into energy in physics. So I start plotting this level, one energy level, second, third, fourth, like that. I can go on putting them as energy levels. Right? Different energy electrons. We don't care where they are in the material. We are putting them and I say these are I'm taking the top two energy levels. It doesn't mean that the electrons are in the top of the surface. They are anywhere in the material. But they have the highest energy. In fact, the lowest energy, but because I take a negative value, it becomes the highest energy. So the lowest energy electrons, I take these top two levels. Now what has happened? You know the Pauli's exclusion principle. What did Pauli say? That all electrons are very egoistic. Right? Every electron is defined by 4 quantum numbers. You all know the 4 quantum numbers. So they say, every electron says, see, I want to have a unique quantum numbers. No two electrons can have all the 4 quantum numbers same. So each of them want a different road by itself to travel. The electron says, every electron wants it. So I can only maximum put 2 electrons in one level because I can take one with the upspin and one with the downspin. So you'll have 2 electrons in one shell. But they again have 2 separate states inside that level. So this one causes problems. Because if I have one atom, like I saw here, which is here, energy levels at this point of time, I have 2 electrons in a particular orbit. Then I bring another atom together. Now I have 4 electrons in that orbit, 6 electrons, 8 electrons. I go on putting atoms together. And eventually, what happens? The number of roads cannot fit in that orbit. Just like our Bangalore roads, you have to go on widening the roads. After more and more people's traffic come, you have to widen. Similarly, these roads, the energy levels widen, and instead of the orbits, they become bands. And this is called as the band structure of solids. And you know that band is a valence band and a reduction band. That is the reason I started by telling 2 boxes. A valence box and a reduction box. And that I told you the gap between them is the energy band gap. For silicon, this gap between the two was the band gap of the material. Now see, what is amazing? Earlier, people studied this part and it was called as atomic physics. Right? Very well understood. Beautiful work. I mean, the J. White book, I think it's amazing. Molecular physics, etc. So studied here. Then you have solid state physics, which was studied here, but what was ignored is this region. There I had a finite number of atoms together. That region is what is called as nanoscience. Right? So what you can see here, see simple here, band gap here was here, this much. Now I make material smaller and smaller, the band gap increases. Right? It's an amazing thing. So that's why I can change the property of the material by just controlling the size of the particle. That is my nanoscience. So if I take a cadmium selenide nanoparticle, and I told you the band gap absorbs that particular color and also gives out a color. That means if I have a size of this one, I have different color, different color, different color, different color. Now, one material can give all the colors. I am only defining one property here because of the year of light. Otherwise, there are all other properties also depend on these kind of properties, which I am not talking about. Right? So now, and also not relevant to the solar cells and the LEDs. So now, I get different band gaps. So if I make a material which is extremely small, cadmium selenide of 1 nanometer, the band gap is very large here. So I get blue light out of it because the energy gap is very large. Then I take go on, increasing, I can get different colors from that material. And ultimately when I make a 10 nanometer particle, I start getting red color out of it because the band gap is little small, the energy is small. So this is what we do by tuning the band gap. And this is well beautifully defined by the particle in the box, which we all study, and when we studied, we didn't even know why we are talking about it. But right now, we understand that there are beautiful states you can create and see. So what do these states look like? Let me take a bulk material in all the three directions. That means it is like a ground, a three-dimensional ground, if you can imagine. You allow hundreds of people to roam around here and there. So somebody is walking, somebody is crawling, somebody is running. You get all the velocities. If you plot all the velocities, it will be a parabolic behavior, a square behavior, right? So statistically it has to be done like that. So I plot this number of electrons versus the energy, with different energy, with different velocity. I can get a parabolic behavior. It is defined in quantum mechanics as E is equal to h cross square k square by 2a. You know the k square relation. So that is that. Now what I do, I restrict the box. I remove, because I could not move in this direction also. Now I reduce this and put a top floor like this. So now I can go around here, but I cannot go around in this direction. I am confined in this direction. And when I am confined in this direction, that means all these paths are not available. So it should have been like this parabolic, but it is not parabolic, some paths are not allowed. And this can be beautifully understood by doing some simple Schrödinger equation solutions. Okay? It's not complicated. That's why I wished when I was studying, I knew these things. I would have enjoyed my physics more. Okay? But we didn't. Okay? It was studied as something very different from real life. That was unfortunate. So we started seeing less paths which are available. So I get this step kind of here. Now I reduce in this hall, I make it even narrow. I put chairs here. Now I have to walk only in this direction. So I can move only in one direction. And that is a quantum wire or a nano wire. When I put that, again further routes are reduced. Number of options are reduced. So I start getting this kind of behavior. Then what I do, I confine in a very small region, what is called as the quantum dot. Okay. So I have no freedom to go. It's very limited inside the box depending on my wavelength. That's what I said in the particle in the box. If I see, then it starts behaving in discrete state, like an atom. It has different dimensions. Now it is becoming closer and closer to an atom by making it small. By making it slightly big, I can make it slightly deviate from that atom. So that's what I do by this part. So that means I'm changing the roles of the electrons, which we were talking about earlier. I'm able to change the roles of these electrons by confining the electrons in different dimensions. Now that is very, very important to understand what happens in nanoscience. And I think this is the most important property of nanoscience. And not many people talk about many things. But in my view, and probably it's true, that this is the one, the electron confinement is the reason why nanoscience is very important. Second thing, this is a beautiful picture. When you make a nanoparticle, as I said, give this example, a sugar cube has 1 centimeter square area, one face, 6 faces, 6 centimeter square area. That means approximately the size of a palm. The surface area of a sugar cube is approximately the size of my palm. Now I break this into 1 nanometer cubes, many 1 nanometer cubes. Okay, each of them 6 nanometer square surface area. But how many nanometers, how many cubes? Enormous number of cubes, because that is cube and this is square. Surface area is a square, volume is a cube. So now by this relationship, I can make the particles smaller and smaller, then my surface area becomes so large that a sugar cube nanoparticles and calculate the area, it is equal to a cricket ground. It becomes solar, the same sugar cube surface area. So this is another important thing. The chemists love this. Large surface area. Can do some beautiful catalytic reactions on the surface. So many things, applications. And not only that, for solar cells, LEDs, I can absorb a lot more light. You understand? I was talking about how to increase from 100% to 200%, 300%. Means I'm making, instead of making films of silicon, now I make clusters of silicon. And with a lot of surface area. That means sunlight can enter in different directions. I can get emission from different directions. So I can get very good solar cells and efficient from this. And then another important thing is, the atoms on the surface are different from the atoms inside. Right? You can see this atom, it is bound on all sides. It's well defined, its position is defined. Okay? It's all by Coulomb's law, everything you have found out where it has to sit, and it has 6 valencies, so all the 6 valencies are satisfied, it is sitting there. Okay? But what happens to the atom on the surface? They don't have neighbors. Right? So inside, somebody sitting inside the chair, somewhere in the middle, has no freedom. But here, you can easily stretch your leg like you were doing. So similarly, these atoms also stretch their legs. And this is called a surface reconstruction. That means the atoms on the surface are not sitting in their well-defined positions. They are randomly distributed. Not only random, but they have a particular structure which are called as reconstructions, which are called as some arrangement on the surface. So now, it doesn't happen only to the top surface. Once the top surface happens, then the second one, third one, fourth one also get influenced by this. So there are 3 to 4 layers of the surface which get distorted. Once the atom positions are distorted, the properties are different. Obviously, you cannot get the same property because how we define our electronic properties is how electrons are distributed in the material. Now, if when the atoms are positions are changed, then the distribution changes, so their behavior changes. So this is another way of tuning the property of the material. Now, so look at nanomaterials. Nanomaterials are groups of say 100 to 200 atoms. So which have only 4 or 5 layers on top of it. If the surface influences 4 or 5 layers, all the atoms are influenced. That means a nanoparticle does not have your bulk property anymore. It has its own property and depends on how you do it. So this is called as the kinetics of growth. Now it is like an example, is a large crowd, you ask them to come together and form a circle. You ask them quickly do it, I will give 1 minute to do it, like the photographer says. Come back to quickly. Then people come and you join together, but a lot of defects will be formed inside the material. But if you give them enough time, okay, to come and join, they can align beautifully and sit in the material. Similarly, in these materials, depending on how we form the nanoparticles, how fast, which is called as the kinetics of growth, over the thermodynamics of growth. Thermodynamics is when the atoms have enough time and enough energy to go and sit wherever they want to sit, which is called as the thermodynamic equilibrium. They go to the best position, like a canteen in a college, right? You all want to go. That's the best place to sit. But teachers don't allow you to sit in the canteen. They ask you to come to the class. So similarly, that is the kinetics of growth. So we don't allow them and make them sit in another position. So from this, we can actually control the defects inside the material. And defect in physics is not a defect, right? It is a good thing. It is another ability. So you can tune the defect, what is called as defect engineering, to produce some enormous things. Again, I don't have time to go into that interesting topic of defect engineering, but let me say that we can also control the amount of defects inside the material, and also we know how to remove the defects from the material. And that is why nano has the 3 fantastic capabilities. One is I can change the loads for electrons, like controlling the size and shape of the materials. Then I can increase the surface area of this material. Okay, and then I can control the defects in this material. So these 3 tunabilities are very difficult to make. Okay, because to get reproducible results in nano is very tough because of so many parameters varying, but at the same time, it is a great opportunity. If anything becomes complex, it is good for us. Then we get our salaries. Otherwise, if something is very simple, the problem will be solved and there will be no physicists in this world. So that is why it is important. More complexities, we love complexity. Right? So we can do that. But ultimately, finally, what is the challenge? The challenge finally is to form a bulk material. What is the use of making nanomaterial? You can treat with a microscope, but you have to make a useful material. I told you, you have to make a chair out of nanomaterials, you can make a camera out of nanomaterials, you have to make a table out of it, you can do everything out of nanomaterials. Because they can all give you different materials. Again, it's not a talk on nano, so I will not spend too much time on that, on the exciting things about nano which are possible. But I just want to tell you that So, but ultimately I have to make a bulk material which has nano properties. What? Because if I take a nano material and put it together again, it will become bulk. It will lose its properties. But the challenge is to keep it, retain its nano properties, but still have a bulk material so that I can make a chair out of it and ultimately a real nano car out of it. Okay, right now it is not there, as I said. So to do that, we need this assembly, what is called a self-assembly. And this is a real challenge. And this is a real challenge, and that is why we don't have so many products yet in nanoscience, though it has been in the market for more, in the laboratories for more than 30 years, but it is not in the market anymore. The only stupid applications are more with the cosmetics. You know, where people talk of that as all stuff of nonsense. And in fact, I heard that the Revlon, the company, has more than 3,000 patents for that. And but the real applications have to come, have yet to come. And because there are some of these challenges of defect control, size control, as well as shape control, as well as assembly. So now, let me briefly, probably take another 10 minutes. Yeah, please. Because unfortunately, I don't see people sleeping, so I can't stop. But another 10 minutes. This is my laboratory. This is a commercial grade. I request you to visit our center. It's an excellent center. Of course, it's on the other side of the world, or Bangalore, in other words. It is Jaipur, near Jaipur. It is one of the best laboratories for nanoscience you can ever see in the world. I can tell you that. In fact, we have the best electron microscope in the world. Okay, there are several, of course, led by the great Prof. Rao. He has built this laboratory, nurtured it, and he still today works for 20 hours a day in that laboratory. So it's an amazing laboratory with fantastic facilities. So CNR keeps telling, when they were doing science, they did not have facilities, so he doesn't want to deprive the youngsters from not having the facilities. So now we have some of the best facilities you can ever think of. So this is, again, please visit whenever it is possible. And then, this is a molecular beam epitaxy. This is the system I use to make these nanomaterials. This is about half the size of this room. It's a huge system. To just make a simple nanomaterial film, we need this system. Again, I don't want to describe it because we have to control every parameter of microarray. As I told you, I change one parameter, the other one will create problems. So how to get reproducible results, we have to do with extremely sophisticated growth. This is called as the molecular beam epitaxy. And this system, what we use, again, it works in a vacuum of 10 to the power of minus 11 torr. Okay, so making the vacuum itself is a big challenge. To tell you what minus 11 torr is, probably, as we can measure only up to 10 to the power of minus 12 in this world now, in the whole universe, the ability to measure. And that's what we think is the vacuum in space. Right? It's about 12 to 13, that's what they say in space. But here, we create about minus 11 torr vacuum. So you usually work in minus 11 torr vacuum. So very high. Why you want to create vacuum? Because in the air, if you see, every nanometer, the air molecules are striking with each other. So a very short mean-free path. That's what we call. Right? But if I create a vacuum, then they're a little bit farther. Then you have a longer. Now if I go to minus 11 torr, the distance between two collisions of an air molecule is probably about 10,000 kilometers. So that is how I can get extremely clean films. That means when I grow, I will not have any collisions with the air molecules inside, and that's why I need a vacuum on this. So, okay, let me cut this short. So what we have done, Manoj and Satish spent a lot of time, hundreds of films, I am not showing all the details. They found ways of making nanomaterials of gallium nitride. People had not made materials by only kinetic control. They had done it by another technique called as the VLS technique, or the vapor liquid solid epitaxy technique. But only by kinetic control, but that involved another catalyst element. So we did a method where we need not use a catalyst method, spontaneously grow nanostructures. And that's what they did. Again, a lot of you will get some nanorods, nanoballs, quantum dots, all sorts of things by this system. Okay, again let me jump. All other structures, we thought first when we formed this kind of a network structure of gallium nitride nanoballs, we thought that some junk, they have grown something very bad. So we wanted to avoid this, but it was so persistent, fortunately for us, that it refused to go away. And we were trying method of eliminating it. To eliminate it, how to eliminate it, we started measuring its properties. And when we measured the properties, we found some very exciting properties which we never expected. And so, for the last 3 years, we are stuck with this wall. We are breaking our heads against this wall every day, and we call it as a great wall of gallium nitride. So this wall, I'll tell you very briefly what it does. So that's why I said research is something like that. You don't do with any intention. Okay, I I now claim that I was working towards LEDs and that and this, but it is nonsense. We just do because we are enjoying doing something. And that is the opportunity we have, better than what engineers do. Engineers are defined what they have to do. We are not defined. They pay us money to do whatever we want to do. That's why they pay us less than the engineers. That is also there. Right? So these walls, they're fantastic. Again, I'll not jump into this. I'll just show you some of the properties of these walls. If somebody is interested, why I'll be showing some of these pictures and telling of them. If somebody is interested, I'll be very happy to discuss. Maybe sometimes you can come out with some ideas which will help me also at my research. Because all these results I'm showing, a couple of them are published, the rest are not published. They're very, very recent results. Okay, and we don't understand them. We are not published because we have not understood them. But beautiful observations. We know observations are real, but we don't know the mechanism involved. We have a speculation, but it doesn't work. I'll try to see if I can take you through this. So now, these walls, we realized, were actually nothing but how these walls were formed. Later we realized that we thought it was just a strain relaxation wall. Then we realized it was actually those screw dislocations I talked about. Those screw dislocations, earlier just threading like this and becoming a dislocation inside the film. Now what we are doing by the kinetics, we are actually opening it up. So these are called as open screw dislocations of these materials. So at the bottom of each of these holes, there is a screw. There is a step. There is a screw like this. The atoms should have been sitting like this, but they sit like this. So there is a step here. That step becomes the nucleation center. So if I can blow something with a different kinetics, then I can actually form a rod through this, a nanorod through this material. Because that screw gives you the step for it to spiral around and become a rod. And there are different kinetics. So we have tried to find out the mechanism, which is again accepted now. It's a new mechanism to grow rods. We can grow many, many rods like this, very, very perfect, single size shaped rods, well self-assembled. As I said, this was done. And then we also found out how to tilt the rods, how to align the rods, all sorts of things. Because when the light, for example, is being emitted, if it is tilted, light will go in all directions. If you want in a certain direction, you have to align these rods. Even for absorption, if the sunlight is there, I need to absorb in that direction. So that is why we learned how to align the rods. Okay. And then we also found that the properties of the rods were not only aligned, but they also have a symmetry, they have arrangement, because it was all defined by the dislocations which are related to the unit cells of the two materials. So that symmetry was very visible in this material. So now, and again we look at some things about the rods. Let me jump this. These are all electron microscope pictures to tell you where the dislocation is, where the stacking fault is, how it is growing, etc. etc. Again, not important. But this slide is very important. See, this is the material which is now used to make commercial LEDs. The best LEDs in the world are made of this material. And we looked at the light emission of this material. And see, that is here, very, very tiny, not visible at all. Then we made these walls and we look at the light emission. Look here, about 200 times larger. Amazing light emission. Nobody expected this. Then we started thinking why? Why does it? Again, and then we did some nitidation and enhanced it further. Now we have a 500 times more emission than the commercial LEDs we have in this market. This is only about less than a 6 months old result. So we think that we may have made a material, but again there is a problem here. The problem is, as I told you, it is not only making the material, but ultimately you have to make the PN injection. And there is a big challenge in that. So probably the next 6 months we will be spending trying to make PN injection, and hopefully we will be able to make those PN injections of this material. We should get some of the brightest LEDs which are possible. Okay, because I forgot to tell you, as I said, the tube light gives you about 70 lumens per watt. LED can give you 763 lumens per watt. So to attain there is a very, very long path. So that is what. So with this, it looks we can break that. Let me take a bulk material in all the three directions. That means it is like a ground, a three-dimensional ground. You can imagine. You allow hundreds of people to roam around here and there. So somebody is walking, somebody is crawling, somebody is running. You get all the velocities. If you plot all the velocities, it will be a parabolic behavior, a square behavior, right? So statistically it has to be done like that. So I plot this number of electrons versus the energy, in different energy, in different velocity. I can get a parabolic behavior. It is defined in quantum mechanics as E is equal to h cross square k square by 2a. You know the k square relation. So that is that. Now what I do, I restrict the box. I remove, because I could not move in this direction also. Now I reduce this and put a top floor like this. So now I can go around here, but I cannot go around in this direction. I am confined in this direction. And when I am confined in this direction, that means all these paths are not available. So it should have been like this parabolic. but it is not parabolic, some paths are not allowed. And this can be beautifully understood by doing some simple Schrodinger wave equation solutions. Okay, it's not complicated. That's why I wished when I was studying, I knew these things, I would have enjoyed my physics more. Okay, but we didn't. Okay, it was studied as something very different from real life. That was unfortunate. So we started seeing less paths which are available. So I said, here this step kind of here. Now I reduce in this hall, I make it even narrow. I put chairs here. Now I have to walk only in this direction. So I can move only in one direction. And that is a quantum wire or a nano wire. When I put that, again further loops are reduced. Number of options are reduced. So I start getting this kind of a behavior. Then what I do, I confine in a very small region, what is called as the quantum dot. Okay. So I have no freedom to go. It is very limited inside the box depending on my wavelength. That's what I said, the particle in the box. If I see, then it starts behaving in discrete state, like an atom. It has different dimensions. Now it is becoming closer and closer to an atom by making it small. By making it slightly big, I can make it slightly deviate from that atom. So that's what I do by this part. So that means I am changing the roles of the electrons, which we were talking about earlier. I am able to change the roles of these electrons by confining the electrons in different dimensions. Now that is very, very important to understand what happens in nanoscience. And I think this is the most important property of nanoscience. And not many people talk about many things. But in my view, and probably it's true, that this is the one, the electron confinement is the reason why nanoscience is very important. Second thing, this is a beautiful picture. When you make a nanoparticle, as I said, give you this example, a sugar cube has 1 centimeter square area, one face, 6 faces, 6 centimeter square area. That means approximately the size of a palm. The surface area of the sugar cube is approximately the size of a palm. Now I break this into 1 nanometer cubes, many 1 nanometer cubes. Okay, each of them 6 nanometer square surface area. But how many nanometers, how many cubes? Enormous number of cubes, because that is cube and this is square. Surface area is a square, volume is a cube. So now by this relationship, I can make the particles smaller and smaller, then my surface area becomes so large that a sugar cube, if I make it into 1 nanoparticles and calculate the area, it is equal to a cricket ground. It becomes so large, the same sugar cube surface area. So this is another important thing. The chemists love this. Large surface area. Can do some beautiful catalytic reactions on the surface. So many things, applications. And not only that, for solar cells, LEDs, I can absorb a lot more light. You understand? I was talking about how to increase from 100% to 200%, 300%. Instead of making films of silicon, now I make clusters of silicon. And with a lot of surface area, that means sunlight can enter in different directions. I can get emission from different directions. So I can get very good solar cells and efficient from this. And then another important thing is, the atoms on the surface are different from the atoms inside. Right? You can see this atom, it is bound on all sides. It's well defined, its position is defined. Okay, it's all by Coulomb's law, everything you have found out where it has to sit, and it has 6 valencies, so all the 6 valencies are satisfied, it is sitting there. Okay, but what happens to the atom on the surface? They don't have neighbors, right? So inside, somebody sitting inside the chair, somewhere in the middle, has no freedom. But here, you can easily stretch your leg like you are doing. So similarly, these atoms also stretch their legs. And this is called a surface reconstruction. That means the atom on the surface are not sitting in their well-defined positions. They are randomly distributed. Not only random, but they have a particular structure which are called as reconstructions, which are called as some arrangement on the surface. So now, it doesn't happen only to the top surface. Once the top surface happens, then the second one, third one, fourth one also get influenced by this. So there are 3 to 4 layers of the surface which get distorted. Once the atom positions are distorted, the properties are different. Obviously, you cannot get the same property because how we define our electronic properties is how electrons are distributed in the material. Now, when the atoms' positions are changed, then the distribution changes, so their behavior changes. So this is another way of tuning the property of the material. Now, so look at nanomaterials. Nanomaterials are groups of say 100 to 200 atoms, so which have only 4 or 5 layers on top of it. If the surface influences 4 or 5 layers, all the atoms are influenced. That means a nanoparticle does not have your bump property anymore. It has its own property and depends on how you do it. So this is called as the kinetics of growth. Now it is like an example is a large crowd, you ask them to come together and form a circle. You ask them quickly do it, I have only 1 minute to do it, like the photographer says. Come back, do it quickly. Then the people come and we join together, but a lot of defects will be formed inside the people. But if you give them enough time, okay, to come and join, they can align beautifully and sit in the material. Similarly, in these materials, depending on how we form the nanoparticles, how fast, which is called as the kinetics of growth, over the thermodynamics of growth. Thermodynamics is when the atoms have enough time and enough energy to go and sit wherever they want to sit, which is called as the thermodynamic equilibrium. They go to the best position, like a canteen in a college, right? You all want to go. That's the best place to sit. But teachers don't allow you to sit in the canteen. They ask you to come to the class. So similarly, that is the kinetics of growth. So we don't allow them and make them sit in another position. So from this, we can actually control the defects inside the material. And defect in physics is not a defect, right? It is a good thing. It is another ability. So you can tune the defect, what is called as defect engineering, to produce some enormous things. Again, I don't have time to go into that interesting topic of defect engineering, but let me say that we can also control the amount of defects inside the material, and also we know how to remove the defects from the material. And that is why nano has the three fantastic capabilities. One is I can change the loads for electrons, like controlling the size and shape of the materials. Then I can increase the surface area of this material, okay, and then I can control the defects in this material. So these three tunabilities are very difficult to make, okay, because to get reproducible results in nano is very tough because of so many parameters varying, but at the same time it is a great opportunity. If anything becomes complex, it is good for us, then we get our salaries. Otherwise, if something is very simple, the problem will be solved and there will be no physicists in this world. So that is why it is important, more complexities, we love complexity. Right? So you can do that. But ultimately, finally, what is the challenge? The challenge finally is to form a bulk material. What is the use of making nanomaterial? You can treat with a microscope, but you have to make a useful material. I told you, you have to make a chair out of nanomaterials, you can make a camera out of nanomaterials, you have to make a table out of it, you can do everything out of nanomaterials. Because they can all give you different materials. Again, this is not a talk on nano, so I will not spend too much time on that, on the exciting things about nano which are possible. But I just want to tell you that, but ultimately I have to make a bulk material which has nano properties. Because if I take a nanomaterial and put it together, again it will become bulk. It will lose its properties. But the challenge is to keep it, retain its nano properties, but still have a bulk material so that I can make a chair out of it and ultimately a real nano car out of it. Okay, right now it is not there, as I said. So to do that, we need this assembly, what is called a self-assembly. And this is a real challenge. And this is a real challenge, and that is why we don't have so many products yet in nanoscience, though it has been in the market for more, in the laboratories for more than 30 years, but it is not in the market anymore. The only stupid applications are more with the cosmetics. You know, where people talk of that, this all stuff of nonsense. And in fact, I heard that the Revlon, the company, has more than 3,000 patents on that. But the real applications have to come, have yet to come, and because there are some of these challenges of defect control, size control, as well as shape control, as well as assembly. So now, let me briefly, probably I can take another 10 minutes. Yeah, please. Because unfortunately I don't see people sleeping, so I can't stop. But another 10 minutes. This is my laboratory. This is a commercial grade. I request you to visit our center. It's an excellent center. Of course, it's on the other side of the world, or Bangalore, in other words. It is Jaipur, near Jaipur. It is one of the best laboratories for nanoscience you can ever see in the world. I can tell you that. In fact, we have the best electron microscope in the world. Okay, there are several, of course, led by the great Prof. Rao. He has built this laboratory, nurtured it, and he still today works for 20 hours a day in that laboratory. So it's an amazing, amazing laboratory with fantastic facilities. So CNR keeps telling, when they were doing science, they did not have facilities, so he doesn't want to deprive the youngsters from not having the facilities. So now we have some of the best facilities you can ever think of. So this is, again, please visit whenever it is possible. And then, this is a molecular beam epitaxy. This is the system I use to make these nanomaterials. This is size, about half the size of this room. It's a huge system. To just make a simple nanomaterial film, we need this system. Again, I don't want to describe it because we have to control every parameter of the product. As I told you, I change one parameter, the other one will create problems. So how to get reproducible results, we have to do with extremely sophisticated probe. This is called as a molecular beam epitaxy. And this system, what we use, again, it works in a vacuum of 10 to the power of minus 11 torr. Okay, so So painting the vacuum itself is a big challenge. To tell you what minus 11 torr is, probably, as we can measure only up to 10 to the power of minus 12 in this world now, in the whole ability to measure, and that's what we think is the vacuum in space. Right? It's about 12 to 13, that's what they say in space. But here we create about minus 11 torr vacuum. So usually work in minus 11 torr vacuum. So very high. Why you want to create vacuum? Because in the air, if you see, every nanometer, the air molecules are striking with each other. So very short mean-free path. That's what we call. Right? But if I create a vacuum, then they're a little bit farther. Then you have a longer. Now if I go to minus 11 torr, the distance between two collisions of the air molecule is probably about 10,000 kilometers. So that is how I can get extremely clean films. That means when I grow, I will not have any collisions with the air molecules inside, and that's why I need a vacuum on this. So, okay, let me cut this short. So what we have done, Manoj and Satish spent a lot of time, hundreds of films, I am not showing all the details. They found ways of making nanomaterials of gallium nitride. People had not made materials by only kinetic control. They had done it by another technique called as the VLS technique, or the vapor liquid solid epitaxy technique. But only by kinetic control, but that involved another catalyst element. So we did a method where we need not use a catalyst method, spontaneously grow nanostructures. And that's what they did. Again, a lot of you will get some nanorods, nanoballs, quantum dots, all sorts of things by this system. Okay, again let me jump. All other structures, we thought first when we formed this kind of a network structure of gallium nitride nanoballs, we thought that some junk, they have grown something very bad. So we wanted to avoid this, but it was so persistent, fortunately for us, that it refused to go away. And we were trying method of eliminating it. To eliminate it, how to eliminate it, we started measuring its properties. And when we measured the properties, we found some very exciting properties which we never expected. And so, for the last 3 years, we are stuck with this wall. We are breaking our heads against this wall every day, and we call it as a great wall of gallium nitride. So this wall, I'll tell you very briefly what it does. So that's why I said research is something like that. You don't do with any intention. Okay, I now claim that I was working towards LEDs and that and this, but it is nonsense. We just do because we are enjoying doing something. And that is the opportunity we have, better than what engineers do. Engineers are defined what they have to do. We are not defined. They pay us money to do whatever we want to do. That's why they pay us less than the engineers. That is also there. Right? So these walls were fantastic. Again, I'll not jump into this. I'll just show you some of the properties of these walls. If somebody is interested, why I'll be showing some of these pictures and telling of them. If somebody is interested, I'll be very happy to discuss. Maybe sometimes you can come up with some ideas which will help me also at my research. Because all these results I'm showing, a couple of them are published, rest are not published. They're very, very recent results. Okay, and we don't understand them. We are not published because we have not understood them. But beautiful observations. We know observations are real, but we don't know the mechanism involved. We have a speculation, but it doesn't work. I'll try to see if I can take you through this. So now, these walls, we realized, were actually nothing but how these walls were formed. Later we realized that we thought it was just a strain relaxation wall. Then we realized it was actually those screw dislocations I talked about. Those screw dislocations are here just threading like this and becoming a dislocation inside the film. Now what we are doing by the kinetics, we are actually opening it up. So these are called as open screw dislocations of these materials. So at the bottom of each of these holes, there is a screw. There is a step. There is a screw like this. The atoms should have been sitting like this, but they sit like this. So there is a step here. That step becomes the nucleation center. So if I can grow something with a different kinetics, then I can actually form a rod through this, a nanorod through this material. Because that screw gives it the step for it to spiral around and become a rod. And there are different kinetics. So we have tried to find out the mechanism, which is again accepted now. It's a new mechanism to grow rods. We can grow many, many rods like this, very, very perfect, single size shaped rods, well self-assembled. As I said, this was done. And then we also found out how to tilt the rods, how to align the rods, all sorts of things. Because when the light, for example, is being emitted, if it is tilted, light will go in all directions. But if you want in a certain direction, you have to align these rods. Even for absorption, if the sunlight is there, I need to absorb in that direction. So that is why we learned how to align the rods. Okay. And then we also found that the properties of the rods were not only aligned, but they also have a symmetry, they have arrangement, because it was all defined by the dislocations which are related to the unit cells of the two materials. So that symmetry was very visible in this material. So now, And again, we look at some things about the rods. Let me jump this. These are all electron microscope pictures to tell you where the dislocation is, where the stacking fault is, how it is growing, etc., etc. Again, not important. But this slide is very important. See, this is the material which is now used to make commercial LEDs. The best LEDs in the world are made of this material. And we looked at the light emission of this material. And see, that is here, very, very tiny, not visible at all. Then we made these walls and we look at the light emission. Look here, about 200 times larger. Amazing light emission. Nobody expected this. Then we started thinking why? Why does it? Again, and then we did some nitridation and enhanced it further. Now we have a 500 times more emission than the commercial LEDs we have in this market. This is only about less than a 6 months old result. So we think that we may have made a material, but again there is a problem here. The problem is, as I told you, it is not only making the material, but ultimately you have to make the PA injection. And there is a big challenge in that. So probably the next 6 months we will be spending trying to make PA injections, and hopefully we will be able to make those PA injections of this material. We should get some of the brightest LEDs which are possible. Okay, because I forgot to tell you, as I said, the tube light gives you about 70 lumens per watt. LED can give you 763 lumens per watt. So to attain there is a very, very long path. So that is what. So with this, it looks we can break the barrier. That's what we think. But let's see. Okay, and then we had another interesting thing. We were looking at the mobility of electrons in this material. Normally in gallium nitride, the electron mobility means how fast they move inside the material was about 300 to 400. But in this material, in the nanowalls, we saw that it has a mobility of 20,000. And when we saw this, we thought there is something wrong with the experiment. We didn't do it properly. But we repeated and repeated and repeated. Now we are convinced it is actually true. And we also know why this happens is again because of the electron confinement. As I told you in the particle in the box, now the layers were very close by, so they would interact with each other. Now I have separated the layers by making it narrow at the tip of these walls. So at the tip of the walls, the electrons travel without any electron interaction. That is how we can get long coherence spins. To verify this, we actually also made some Bangalore resistance measurements and collaborated with IIT Bombay for this. Professor Dhar, he works on low temperature, high magnetic field measurements. We did some and showed that there is a presence of a weak localization, okay, which can give us this high mobility. Now we are looking at D-Shubnikov of oscillations, which will confirm whether these are 2D electron gases or they are 1D electron gases. So we are working on that, and we are also doing and collaborating with my colleague Professor Jawaharla, who is doing some theoretical calculations on this DFT calculation to find out whether it is a feasible thing or not. So we are trying to understand this. And then another surprise was we could see magnetism in this, ferromagnetism in this. It was behaving like iron, copper, nickel, cobalt, nickel. We were surprised because there are no free electrons in gallium nitride. I told you, in a gallium nitride, on its own at room temperature, my rods were empty. There are no free electrons. Only in a metal there are free electrons. Here there are no free electrons. So you are not expected to see magnetism in this material. If you remember a few years ago, I mean, some of you may be aware, about 2007, 2008, Professor C.N.R. Rao came up with this fantastic theory that if you make the particles small enough, then the dangling bonds produce magnetism in these materials. And this is a highly cited work in the last few years, but at the same time highly criticized. It is 50% people say it is great, 50% say it is not great. So we wanted to see whether it is true in our case or not. We wouldn't have even tried magnetism with this material. But just because that was very hot at that time, we thought we would try to do this. And we saw the magnetism. Then we wanted to see if it is because of an impurity. Such a thing can come with it because of an impurity. So we did what is called as the MFM, magnetic force microscopy studies, which will tell you locally where the magnetism is happening. And we found that all the walls, the tips of the walls were magnetized. And that, again, this result nobody wanted to believe. So we took more than a year to confirm that it is actually magnetism, because we were scared to say that. And now we are pretty confident. I did some experiments and I went to Northwestern University to perform some special experiments. These are the results from there. And then we showed now for beyond doubt that there is magnetism in these materials. Okay, so that magnetism is important. Because why magnetism? See now, a very important thing. We know of electronics, we know of optoelectronics. But the future is what is called as spintronics. Because for spin, now the electrons we think there are only two spins, up spin and down spin. That is why we say binary numbers 0 and 1. Whether electron, no electron, or up electron, down electron. That is enough. But we want to teach the material. Look, boss, there are other things between 0 and 1, which we know but you don't know. So we want to tell it, instead of up and down, we would also like to tilt the spins.
and transport this tilted spin across the material. And then I can have different information with different tilt. So you can carry with the same number of electrons, you can carry a lot more information. And that is what is expected for quantum computing and for spintronics, which will be the future. So people are working on this. So what it requires is a semiconductor with a magnetic property. That is what elusive for so many years. But so what people have been doing, they have been trying on this, and they have been putting metallic particles, magnetic materials, inside the semiconductor, doping it with that to create this. But there are a lot of problems with it. But we think we have made a material which is on its own spontaneously magnetized because of this surface free electrons, because of the electron confinement effect. So again, we have to fight our way through and confirm that this is actually true. Again, I'll jump this. Again, another interesting thing, as I told you. So first we have enhanced it about 500 times. Now what I do is I put silver nanoparticles on top of this material. This is the picture I showed you in the beginning. That we have put some silver nanoparticles. And I told you in the metal nanoparticles, there are plasmons. Electrons, oscillating electrons. The plasmons. So if the electrons are oscillating, that they are giving energy at some state and taking energy. So if I can make the light from the material go through these plasmons, they may also get an advantage of energy. So there may be a plasmon band-edge emission coupling. And this coupling was possible, and we could produce even another 5-6 times higher light. So now we have almost about 700 to 800 times larger light than what is used normally in the LEDs right now. So this is showing that, so what I can, if I calculate the efficiency, which we are not able to because of some experimental limitations, we think we can go to that more than 100% efficiency. That with these applications, we are able to go and get the coupling from the material and get maybe something like 400 to 500% efficiency. Again, we are working on that. Hopefully next year I'll be able to give you some results of this. Okay, so this is now another interesting thing. You all seen these beautiful colors of butterflies and peacocks. Their color is not like the color of our shirt. It is not because of dyes. It is because of structural color. If you look carefully by microscopy inside these materials, there are beautifully organized holes in this structure. And the light comes because the light is trapped inside the holes. And the size of the hole is of the wavelength or of the order of the wavelength of normal light. So when you see in different directions, different colored light comes out of it. And depending on the sunlight in which direction, the color of the beautiful peacock and the butterfly changes. And these are motivated by this. People are doing what are called as photonic crystals. So these are fantastic materials. Just like electronics, photonics is a parallel field. Okay. Just like electron band gaps I showed you, there are photonic band gaps. Okay. There are similar phenomena. So, and this field of research is called as, or used, is called as photonics, like electronics photonics. Only problem is, there the dimensions were few angstroms, or fraction of a nanometer, and here it is a few microns. The dimensions are different, but the physics is very similar, and except one more change is that electrons are charged, photons are not charged. So there are some advantages in packing, that's why we use optical fibers, etc., etc. Again, I don't have time to get to that, but exciting field. So we thought that this material, when we made this holes from the top, is also going to be a photonic material. Because we have holes of different sizes, we hope to get different colors in this material. So we tried to look at how the light is coming out of that, but unfortunately we did not see any colors. We see only one color in the wavelength, and which was the same, which was negative. Then we worried a lot, because we expected the confinement to give different colors. Why did it give? Not only that, the even more surprise was that, this was a disappointment, but the surprise was that actually light came from the holes and not from the material. I was expecting the light to come from the material, but it is actually coming from the holes. So we did a cathode luminescence mapping to find out it comes from the holes. We were surprised. Again, we have spent the last maybe 1 year trying to understand this. Now we have a speculative idea of what happens, but I'll talk. But very interestingly, then I go to low temperature. I go to liquid nitrogen temperature and make this measurement. Then the light comes from the walls. It doesn't come from the holes anymore, which is very exciting. Because you can look at this as the beams of very high intensity ultraviolet lights. It means it's very difficult to make a small laser. But here we are able to do something which looks like a laser. It's not a laser as far as we know at this moment, but it is probably not just spontaneous emission. There is some sort of a stimulated emission in this. We are trying to find out why it is happening. So that light is coming out. So this will be very nice if we can make a pattern of this. they are again doing other things related to it. So why is this happening? So we think what is happening is there are electrons on the surface because of the confinement which behave like a metal. If there are free electrons on the surface which gave us the magnetism related to everything, so those electrons reflect the light inside. They don't allow it to go through. So that is why in one case at room temperature you have things going through the material because of the refractive index and reflecting because of total electrical reflection. And in the other case, now the metals, when you go to low temperature, the phonon, the atom vibrations become smaller and smaller. So when the phonon vibrations come, then the electrons become free. They are not bothered by the phonons anymore. So when they become more and more free electrons, they behave like a metal. So it will have a metallic surface on the surface which will reflect the light inside. This is our speculation. Okay, so we are planning to actually understand this in the next few days. And then we are, as I told you, ultimate problem in this is indium nitride. Now we are able to form indium nitride films, etc. on this material. Now I think I have to jump all this. We also have made, by using this as a template, a material which is defect free. Okay, which I told you it's very difficult to reduce the dislocations. See, now the dislocations have stopped here and we have made defect free materials by using my nano network as a template. And then we have seen microscopy and shown that the dislocation comes up to here, but it stops. It doesn't move beyond that. So that is why we are able to form dislocation-free materials, which means that it can be, that huge light which we are looking for in LEDs and the super efficient solar cells may be possible. So we work on this. Again, I jump all this and show that we are also for indium nitride. We have found very high mobilities, the best you can think of for these materials because of the wall which very serendipitously occurred to us. We didn't plan it. So that is giving us very high quality results. And the last example is, then we put the silver nanoparticles and I said this enhances. So then we know that Raman effect, the Raman effect detects, it gives you the fingerprint of molecules. It can tell you which are the bonds, how are they oscillating, all the vibrational spectral bonds are seen by Raman effect. Then there is recently in the last 10-15 years something called a surface enhanced Raman spectroscopy. I'm sure Raman would have been extremely happy to see this. Because now the signal is more than 1 million times larger than the normal Raman signal. The problem with Raman is the cross section is so small that it is very difficult to use it as a regular course. But with surface enhanced Raman spectroscopy, by coupling this with these silver nanoparticles or metal nanoparticles on top of it, you can enhance the signal by 1 million times. So that we try to do that to see, because this surface area was large, we could put nice silver, etc., etc. Again, I don't have details to explain all this. But see, this was my normal Raman spectra. And look at this spectra when I put this as a surface on the silver. So we got an amazing enhancement. These are well-known experiments. Nowadays, a lot of people do this as surface enhanced. But we think we have something a little bit unique with that. Again, I am collaborating this with my colleague Jawaharla, who works as a Raman expert, and trying to see optimize this. So we are actually able to get an enhancement factor of 10 to the power of 80. Okay, and also you can detect very low concentration of 10 to the power of minus 10 molars, which is very useful for disease detection, cancer detection, HIV detection. Because cancer detection, if it can be detected very early, it can be treated. But we know it so late that we have to give an extremely high dose of antibiotics, which is called as chemotherapy. And and finally you don't know whether the patient died because of cancer or because of chemotherapy. There are so many effects of that. So it will be lovely to see if you can detect it much earlier, 3 orders of magnitude earlier, then we can give just enough antibiotics to cure the disease, plus at the same time. So this is again another work which we are trying to do with these nanowalls, which are giving a lot of these nice results. And now we are trying to do, as I told you, we can actually combine indium, gallium, nitrogen and get different band gaps from the same material. Okay, not only nano, but also by alloying. That is a technique called as band gap engineering. And we are trying to do that. We have made nano rods, but we are not able to make good nano walls, you can see here. We are struggling to make the nano walls, and hopefully we should be able to do it soon. We are trying to understand how to do that. We've been struggling for more than 4 months now. So he's struggling to do that. So hopefully we should make this then. If we can make in-gap nano walls of exactly the same morphology as we got earlier, I think it can again open up another few dimensions of this material. With this, I think, as I said, it is the Great Wall of China, gallium nitride, which we are breaking at every day, but it's very, very exciting, something we've never planned. Okay, and we are there working on that. Because earlier, when Professor Rao gave us the money, a lot of money, to set up this facility, we would ask, Professor Rao is like that. We give as much money as you want. Okay, then from tomorrow you will ask where are the results. And that is and he works like that. And so we can't complain. So even at the age of 83, he is the youngest man on our campus. Extremely works hard. So with that, he used to ask, where is your LED? Where is your LED? Fortunately, we couldn't make LED because we were stuck with these walls. But fortunately, we got some interesting physics problems to deal with. Whether they become useful products or not, I don't care because I enjoyed doing this work. I thank all my collaborators, Professor Rao, of course, for all the facilities, the first thing, and his motivation. His presence is such an amazing thing. And then the Kuprani, Babare, Chandras, whom I collaborate. And here are the people who actually work, the students. I only give these nice talks and run around. But basically, these are the people who do the experiments. Praveen, Manoj, Jitesh set up these experiments. Now they are all doing postdocs abroad. And Satish, Malli, Varun, and Darshana, it is their results I presented today. Okay, and then Arpan, Sanjay, and Shivakumar are trying to take this work forward. And then I work with extremely sophisticated equipment, as you can see. So it is not easy to perform these experiments and maintain this equipment. So I really, very sincerely thank Jay, Srinath, Selvi, Kishore, Somsekhar, and Mahesh, who are our technicians who maintain this special equipment for us and who gets the reading for us. And I thank you all for your kind attention. Thank you.
Good evening, ladies and gentlemen. It's my privilege and honor to thank you, sir, for giving an exact talk on light harvesting for super efficient solar cells and LEDs. That's been very informative and interesting talk, sir. On behalf of Bengal Science Forum and all of us here, I propose vote of thanks to Dr. S. Tomorrow's talk by Dr. Vijay Lakshmi Parayasindhi, Professor of Cardiology, C. JDO Institute of Cardiovascular Sciences and Research, will be speaking on Samrata Deshikar, Sarkar Hridaya. All are cordially invited. So, any questions, please?
With regard to light harvesting,
Sorry.
white LED,
White LED.
I think is it possible to recycle the going waste light somewhere in stadiums like from the halogenated light to charge the solar cells?
I didn't
Have you got my
understand.
point, sir?
Recycle what?
I mean the halogenated light they are using in the stadiums.
Yeah.
After that, the light goes something waste, light energy. Is it possible to make use that going waste light energy
what you're
to
telling
charge
is-
the solar cells?
Okay. So if I understand you correctly, you can't charge solar cells, but you can charge batteries. So what you are telling is, the light which is coming, can you also convert that into solar, into energy by solar cell and save it in a battery? Is that what you are saying? Because
artificial light that you are using at the stadium.
yeah, like this is an artificial light. Okay, light is falling. Some light is not being used. Even the stadium is much more. So what you are trying to tell is, can we also convert that light into electricity so that we can charge something? Of course.
Solar cells, what are you making?
No, we can't charge solar cells because solar cells produce the electricity. We have to charge them in batteries, right? So now can we charge batteries so that later we can use? That's the question you are telling. I agree, but the question is the intensity of this light which is coming is very, very low. Even in that stadium, if you look at it, it is ultimately when it reaches per square unit area, it is much, much lesser than the sunlight we get. So it may not be efficient. And if we do that, then we will be blocking the light where we want it to be light. Right? So if we have to do something very close to the lights, I can put a solar cell and get some energy out of it. But what is the use? I'm first getting electricity, then I'm again converting into electricity. Right? So I'm losing in the process and also I'm blocking the light. So if I put the light, for example, in a stadium on the ground, it is too little. I can't produce anything. I will need kilometers of light like that. So that's why the solar energy is freely available. So that is why we have to convert the solar energy and save it in batteries for right utilization of light and to run these lights. But I don't see that we have enough intensity per unit area to produce enough energy to save and become economically viable.
At least for the timing at a smaller scale.
Yeah, we can talk about it later.
Particular area.
Sure. Yeah. Interesting. Yeah.
How does this organic
LEDs. Yeah. Okay. Yeah. Okay. His question is, you talked about inorganic solar cells.
But there is another field which is called as organic electronics, which is become very, very important in this world. Okay, it was started by Shivaprasad. A very interesting story there. Shivaprasad was doping his organic polymers with some dopants, and he went for lunch asking his assistant to put some micromolars of some material of the dopant material into that and annihilate it. And by the time he came back, he saw that the material was very shining and looking like a metal. And then he was surprised what it is. And then he found out what it is, because normally if he had that, he would have scolded the assistant and did a Nehru experiment. But he was very curious to see what it was in Japan. And then he tried to see, he put a multimeter and saw it was conducting like a metal, the polymer conducting like a metal. He was surprised, and that led to the discovery of the organic electronics, and which has given some amazing field in the last 15-20 years. I think they are amazing. You make LEDs, solar cells, everything out of these metals. You can make semiconductors, insulators, transistor, metals, everything through this organic route. But there are two problems. One, its efficiency is very, very, very low. I will show a graph. Like our efficiency, as I said, was 44%, silicon was 21%. These efficiency are 3 to 4%. Okay, so it is very, very low. Not only that, if every half an hour you ask what is the efficiency, it will reduce. The stability is also very less. So the idea is efficiency is low and the stability is low on these materials. But enormous research is going on to enhance the stability. Some people now have claimed up to 10% efficiency on these materials, and with the lifetimes of a few months. Okay, especially Richard from Cambridge University, he started this, and not only that, immediately after he found this, he started a company. This is the Western style of making money. So anyway, he started a company to make these solar cells, but still there is a long way to go on that. But eventually, it will be very big, because though efficiency will always remain like that, very, very low. But it is advantage because it's very cheap. You can actually, what you can eventually do is, you can make this material and mix it with your paint. And you can coat the walls with this paint, and it will become an LED and it will give light. Okay? And you can paint the outside of your wall and make it as a solar cell. You imagine, because of that cost, it can become very, very efficient someday. But at the moment, there are a lot of serious problems in both in efficiency and more than that in terms of stability.
How does the band gap compare?
That's what I said. There is a very interesting method. The electron transport is not like here. It is called because of the polaroids, or what is called as the Perel's distortion. Okay, I'll need a little bit of time to explain that. But if you look at Perel's distortion, maybe we have that universal guru called Google. You can Google it. He can tell you everything about it.
Professor, you are talking about the organic material. This one Stanford team has been studying about the photosynthesis effect of both the bacteria as well as the plant, and then they are thinking that that way throw some light about harvesting even in this type of.
I agree with you. I'm not an expert in the field, but I know that that's what is happening. I should also tell similar things are happening even in organic materials. Professor C.N.R. Rao, in the last 5 years, he has been working on water splitting by using these kind of materials. Okay, where you can bring the water and split from hydrogen and oxygen, both to produce hydrogen, just like how the plants do. And if you look at the plants inside, you have magnesium cubes, which act as catalysts to break this bond. So he's also putting magnesium. Now he has found other ways also. He has found some very extremely interesting results.
But they are converting it to chemical energy only. But finally we have to come to electricity.
No, there are different approaches to this problem. One is a chemical route, one is a semiconductor route, and one is a plasmonic route. So all the three are used for water splitting. As far as I know, that I am not an expert in that.
Thank you.
Nowadays, solar panels they are offering in the market, solar panels and solar, these LED bulbs are also available. What is their efficiency?
That's what available. I said they are of the order of 30 to 40 lumens per watt. 30 to 40. But as I said, the capability is 763 lumens. That is where we are very, very still far away from it. The best ones, which are grown on silicon carbide rather than sapphire, are the ones like, for example, you know, the Audi car. And use some LEDs at the bottom of that. So they are very much more efficient. They are about 70 to 80 equal to the tube lights. Okay, so they are so efficient. Now they are using that on silicon carbide also for the flash of your mobile phones because they want more efficiency on that one. But still, there is to make it commercial and ultimately to replace all these bulbs, the efficiency should be 150 lumens per watt. We are still one third of the way. I mean, 2/3 of the way to go to reach that one. Once we reach 150, it will become economically feasible for us to replace all the lights here. the street lights, all that.
Sir, you are telling the LED emits only white light. So, what I wanted to know, if this LED light is subjected to spectrum, will we get all the colors?
Absolutely. See, that's the whole idea. The LED does not emit only white light.
Yeah.
It does red light, blue light, green light, any light you want. Okay, that's what. But then what we are telling is by combining some, we can get white light. And that's why I said if you combine them in the proper proportion, if you look at the spectrum, it should be like sunlight. But we have not yet attained there because right now we are using blue light and putting yellow phosphorus on top of it. But eventually if we can make three LEDs combined together, as I said, the problem is the green LED. And if we can solve what is called as a green group problem, when you put current, the indium segregates into clusters. It breaks away from the bond. So that is why that is one of the major problems. If we can sort out that problem, then what you are telling is right, we can get exactly the solar spectrum in our area. And that is the aim. So hopefully in the next 5 to 6 years people should achieve this.
Sir, my second question is, there are monocrystalline and multicrystalline, and next one is coming the amorphous one. Which one will be has more efficient?
Silicon has this. What you are telling monocrystalline, polycrystalline and amorphous silicon have already been used.
Yeah.
All the calculators you use are not used amorphous silicon.
Yeah.
Okay. All the solar cells you see in the market are multicrystalline.
Yeah.
Okay. And polycrystalline's efficiency are very low, but they are used for specific purposes. But that problem doesn't come here. We have to have here single crystalline. And that is why these techniques are very expensive and difficult to replace.
Which will be the next one which is coming more efficient in the market, sir?
It's already showing more efficient, but as it is expensive, we can't make it. We cannot come into the market. But again, I'm trying something just in the air. We are trying to see how to make it cheap by making some PDMS tabs of this. Okay. It's a long thing. I'm trying to collaborate with my colleague Kulkarni to see if we can make cheaper, but we don't know.
Thank you, sir.
Sir, instead of making
This is where the brightest question will come from. Yeah.
instead of we clearing the defects in the crystal, how about using the defects for our advantage? Is there any research going on in that?
Absolutely. Beautiful. That is what I thought we did in our work. What we use the defect as nucleation centers to open up the defects and form the walls itself. Now, so the walls are defect free. That is what we have done. So, like the most naughtiest student in the class will be made as a monitor so that he stops making noise. So the same thing we have done. We have taken these screw defects and then opened up the kinetics so that the defects don't act as defects but only act as nucleation centers for making our wall. Very good question.
And another question, sir. We see that the peacocks and the butterflies have a beautiful color structure on their body. How would we creating those color structures in order to utilize as to the other energy source so they can store the energy and produce the result thing?
Absolutely, that is being done. Photonic crystal research is all about that. If you Google it, you will find some fabulous things which have been done in that direction. Because again, people have made it. It is very easy to make a butterfly. We were only motivated by that. Now it is very easy to do that. We know what it is. So now beautiful work is being done and what you are telling is already being done.
Thank you, sir.
Okay.
So we want you to come into this field and do something.
That's the last question.
Yeah.
We will stop.
The last question is he's asking is when will you stop?
Sir, you don't have any questions?
No.
Okay. Thank you.
Nanti yo, berarti.